I'm not going to discuss today, but this is the setting. But of course, you can't forget about.
Tomás, I thought beta was a constant. It has parameters in there.
No, beta is, this is the identity. So beta is this matrix, this 1, 1, minus 1, minus 1. So identity and minus identity. So the important thing about this operator is that if you do the square of this guy, you get minus the Laplacian, and therefore it's very easy to now do the square of this matrix. This works.
I'm sorry. Another question. It's not true that the square of the Dirac operator is the Lambertian.
Well, not here because the Lambertian involves time. Here I'm just considering space.
Oh.
So yes, if you do the Dirac operator with the space, then you are gonna get, yes, this operator. But I'm just gonna consider, say, the spatial Dirac operator, which is this guy here. So here, when I take the square of this operator, what I get is minus Laplacian plus m squared. So in a sense, the Dirac operator here that I'm considering is a local square root of this operator. And this is something that is important for several reasons, to have like a square root, which is a local operator, but the price that you have to pay is to use these matrices. Okay, so why people is interested in this guy here? So of course, the story goes back to Dirac, that when he wanted to describe a relativistic motion of particles of spin 1/2. So this is the thing is that he wanted to combine the relativistic theory with the quantum formalism. So then the first idea is consider the relativistic energy, say, and then just you do the usual thing that you do in quantum mechanics, that is replace your quantities by differential operators. So I replace the energy by derivative with respect to time, and this the moments, but by gradient and some physical constant that I don't care. And if you do that, you end up with this so-called square root Klein-Gordon equation. So you have here this square root of this operator. But if you do this, you end up with a non-local operator. If you do this square root, like for instance, in the Fourier space, for instance, and this was something that it was not suitable for the models that Dirac wanted to describe, and also there were other implications. But the important thing is that he wanted to describe this property of particles, that is the spin, and he wanted a model that described this thing. So what was his idea? So his idea was, okay, let me consider a linearized energy, so energy of this form. So we have now linear in the piece. Here this is constant, and then you want to impose. You want to find alpha and beta, so that this equation is satisfied. So you have really the relativistic energy. And then if you play with this, and you can do it in your free time, you are going to realize that this is not possible if alpha and beta are complex numbers. You cannot do it. But then this is possible if you consider matrices. And then the simplest choice in R3 are these matrices that I just described. So if you take these matrices that I described, you can manage to do this, and you end up with this operator that I described in the previous slide. So this was essentially the origins of this Dirac operator and why it appeared. So these are the main properties. So first, as I told you, this is like a square root of this operator minus Laplacian plus m squared. That it's an operator that it's a 4 times 4 matrix operator and acts on 4 component wave functions. But the introduction of these Pauli matrices, these matrices that I showed you before, it seems that it accounts for the algebra of the spin. So they really show you when you work with them these properties of the spin. That of course I'm not going to talk about this today, but this was something that that Dirac was looking for. So this was a success for this approach. And then another thing that is quite surprising and was of great importance is that this operator has negative eigenvalues. And if you remember from quantum mechanics, the eigenvalues of our spatial differential operators are related with the energy levels of our systems. So if we have negative eigenvalues, this means that we have negative energy. And this was somehow like a proof that there exist states with negative energy. And indeed, years later, it was proved experimentally that indeed this is true. And there exists this thing that is called an antimatter, and where you have particles and antiparticles, and you have things with positive energy and things with negative energy. So in a sense, the Dirac operator anticipated this discovery, this experimental discovery. So okay, for all these reasons, the Dirac operator has been quite popular among the mathematical physics community because of all of this, because it's used to model several things like these antimatter things, and in particular relativistic motion of particles like quarks or electrons. Okay, so now let me go a bit more closer to my problem. So what I want to study is this Dirac operator coupled with a delta shell potential, what is called delta shell potential. This is considering just a potential, but this is going to be a delta distribution supported in the boundary of a set. Okay, so and in particular, what I'm going to consider is this kind of operator. So I have here the Dirac operator, and then I'm going to have like two delta shell potentials. One is going to be with this is just a constant and with identity, and then another constant times this matrix which is beta, that was identity and minus identity. So these two potentials account for modeling electrostatic and Lorentz scalar potentials, so they have important implications in the modeling for this operator. But what really interests us is a special property when these two constants here are in a special relation. Because what happens here, and this is something that it's called in quantum mechanics Klein's paradox, is that if you put a potential which is a delta, in classical mechanics it's like putting a wall that you cannot cross, so particles cannot cross. But in quantum mechanics what happens is that particles with certain probability can cross this kind of walls. And this is what is called Klein's paradox, that you put a wall, but even though particles can cross these walls.
Well, in quantum mechanics, this is just tunneling effect.
Yeah. But
and also you can put a Dirac delta, but you can also put some constant, which is some coupling constant, multiplying this operator, and this theta, and maybe in the behavior should depend on delta, on lambda, on this coupling constant.
Yeah, of course. Actually, what I want to talk about is a particular relation of these coupling constants, because the thing that I'm interested in is precisely when you don't have this phenomena. So, and this is something that I'm gonna skip this, but this is something that was proved that if these two constants are in this suitable relation, then this situation that I said before is not happening. So particles inside your domain that start in your domain never leave the domain for any time, and particles starting outside your domain never enter into your domain. So you have this confinement phenomena, and this is the situation that is interesting, or one situation that is interesting because this can be used to model confinement of particles. Okay, so this is the situation that we want to consider. And in order to consider this, just let me do just a technical thing, because since I have here two constants and one equation, I just want to get rid of one equation. And in particular, it's very suitable to reparameterize these things with another parameter that I'm going to call tau. And I'm just going to call these two constants like two hyperbolic sine and two hyperbolic cosine of tau, since this is essentially the parameterization of an hyperbola. So this is just something that is suitable for a clear notation, because as you saw, the notation is quite messy here. So everything that simplifies things helps. So now I have just one parameter, and then for each value of this real parameter, I have an operator which accounts for this confinement. Okay, and what happens here in this setting is that indeed the operator that I presented before can be decomposed into two operators, one that acts on functions defined in omega and one that acts on functions defined in the complementary. So this is just the confinement represented mathematically. So I can't just consider the operator on functions defined here, because functions are going to have their support essentially in omega. Okay, and the rigorous way to do this coupling of this differential operator with a Dirac distribution is by using boundary conditions. So the rigorous way to deal with this is just consider the Dirac operator acting on functions that satisfy a suitable boundary condition. This is equivalent of to the operator that I was describing before, and this is the setting. So I'm going to have an operator that I'm going to call its tau. So for each value of the parameter, I'm going to have an operator which is defined for functions or acts on functions that are in H1 and that satisfy this boundary condition in the boundary of my domain. I'm going to comment on this in a second, so you can just ignore this. And the operator is just the Dirac operator. So inside my domain, it's the Dirac operator, and then you have this boundary condition. And now let me go a bit closer to this boundary condition. So if I write these things, that remember that these are four component vectors, and these are matrices. So if I write this in a matricial way in this two component fashion that I like, this is just this. So here you have this tau and this sine, hyperbolic sine, and hyperbolic cosine that are from this coupling constants, and then I have this quantity here, which is just the Pauli matrices times the normal. That is, this is n is going to be always the exterior normal of my domain. And then if I just write this, I just multiply these matrices, I end up with this boundary condition. So I have that u is going to be e to the power minus tau times this kind of normal thing times b, and b is going to be exponential and this normal times u. So this is somehow the equivalent thing in this business of the Robin type boundary condition. Since this operator here, this multiplying by sigma times normal, is kind of the normal derivative in this problem. Okay, so here I'm relating my function with the normal derivative of my function, but I'm changing the component. This is a bit more complicated, but you can think like the relativistic version of the Robin boundary condition. Okay, so this is the problem that I want to or the operator that I want to study. Okay, And what is our motivation? Because our motivation, so let me just write it here, just for having it. So my problem is going to be this. So I'm going to have M, I'm going to have this minus M. I want to study an eigenvalue problem, so I'm going to consider this in omega, and then with the boundary condition, which is U and B equals to I, and then I have E minus wrong, sigma normal B, and E now. This is the eigenvalue problem I want to study, and why I want to study this? Well, there's our main motivation for our work comes from physics. From I don't know if I can take this out or not. Well, here it's written the MIT Pak Model. This is a model that was proposed obviously by people from the MIT, which was proposed to model confinement of quarks in hadrons. So this was a model for confinement, and this MIT Pak model corresponds to taking tau equal to 0 in this family of problems. So the family of problems that I want to consider includes this important problem in mathematical physics that many people is interested in. So this was a model that it's used for the confinement of quarks, but its version in R2, it's also useful in material science because it's used in the description of graphene. Okay, so this operator also is used in this business. So a lot of people is interested in the MIT Pak model. So, and the question for the MIT Pak model is the one that I told you before, like, which is the optimal shape? Meaning that if I consider this eigenvalue problem for tau equal to 0, and I consider the first positive eigenvalue, because remember that here I have positive and negative eigenvalues, and I consider the first positive eigenvalue, which is the domain among all of the domains that have the same measure that has the smallest first positive eigenvalue. And so this is the problem that we eventually want to solve. And our approach or our proposal for this is, okay, let's just try to study this more general problem. So we put this MIT operator into a family of operators and try to study the whole family. And okay, you will see in a couple of slides that why this can be useful, or we expect this to be useful, because a priori we are dealing with maybe a more complicated problem. But the thing is that like including this operator into this family, we can somehow connect this operator with other known operators such as the Dirac Laplacian, and then infer some properties of the Laplacian, like transfer them to all other operators of this family. Okay, so this is what we want to do. So okay, so this is enough for the motivation of the problem. But so now let me start with the real business. So now let's just study this problem, and since this is something that at first glance you may not have any intuition, neither me, but then the first thing that one has to do is to do the simplest case. And the simplest case is the sphere. So let's just consider that omega is a ball, and then you have a boundary condition in the boundary of the ball, so the sphere. And here we can do the classical strategy, that is use separation of variables. And the good thing is that this works. And the key in this thing is that there are what are called spherical spinors that are somehow like the generalization of the spherical harmonics, but for this Dirac operator, that are functions that depend on the angle and that generate invariant spaces for the Dirac operator. So And in particular, the notation is a mess because you have here a lot of indexes and like half indexes. Then for each half index, you have like a plus and a minus. And then for each of these, you have an mj that accounts for the multiplicity of the eigenvalues in this eigenspace. But okay, you have that. You can split or decompose your space into a direct sum of these spaces. So for each half integer, then for each nj that goes from minus j to j, and then you have two, one with the plus, one with the minus, that are spaces of functions of this form. So you have a radial part, and here you have the spherical spinor, this with the plus and this with the minus, okay? Or the other way around if you consider the minus. Okay, just I know that the notation is a mess, but just keep in mind that you have for several indexes, you have an invariant subspace that is formed by functions that have radial and spherical parts separated, and the spherical part is just one of these spherical spinors. Okay, so the good thing about this is that since these spaces are invariant by the Dirac operator, then when you want to look for the eigenvalues and you write down this equation, then you convert something that at first glance it's difficult to Bessel type ODs for these radial functions f and g. So this is essentially the same as one does for the Laplacian, for instance, but in a more fancy way with matrices and things more complicated, but it's essentially the same. So we are reduced to study two Bessel type ODs. And then if you solve these ODs, you can find an equation for the eigenvalues, right? So for each value, remember that here I have a parameter that is this tau, and for each value of the parameter, I have an equation, and I find equations for the eigenvalues. And since all of this is explicit because Bessel functions are quite studied and you can have it on your computer, you can plot things and get something like this. So what is this? Here I'm plotting for each value of tau, I'm plotting the eigenvalues. So you see that for tau equal to 0, for instance, I would have the intersection of all these curves are the eigenvalues for this operator. So for another value of tau, I have another set of eigenvalues. But the good thing that you see here, you already see, you see things that are a mess, but you see things that you like, or that are like significant, right? First of all, you see here that there is a gap around 0, that actually this is the mass, that here I am taking it to be 1. So from minus m to m, I'm not going to see any eigenvalues. And then what I see is that above and below, I can somehow parameterize my eigenvalues by this parameter as increasing curves, right? And these curves seem to, some of them join, you have some of them that cross, some of them that converge to the same point. So this is something that I want to understand a bit better, okay? So let me try to do, because this is like a plot of a lot of eigenvalues at the same time, so let me try to do this more step by step. So let me just consider one of these invariant subspaces that I showed you before, okay? So I'm gonna take the first index, j equal to 1/2, then I'm gonna take the minus, and then I'm gonna take, this is gonna be the multiplicity. So this is gonna count for the multiplicity of the eigenvalue, but actually in this case has multiplicity 2, okay? But actually this complicates things a bit more, but anyway. So if you take these indexes, you write your equations, and you end up with this eigenvalue equation. So you impose this, and then you end up with this equation, okay? In which you have here the Bessel functions involved, and here you have the lambda that is the eigenvalue, and here you have tau that is your parameter. And then the idea is, okay, I want to try to do something that, as I showed you, I want to write lambda as a function of tau. So what I need to do is to invert this thing, right? So I call this h of lambda, and I want to invert h. So if I want to invert this, I need to be careful because this goes from 0 to plus infinity. So I need to be careful about the zeros and of these two functions. So I'm going to be able to invert this thing between two consecutive zeros of these two consecutive Bessel functions. But this is something that you can do because two consecutive Bessel functions have zeros that are alternated. So you can do this, and you just need to be careful on the sign. But the sign of this quotient is going to be somehow compensated with the sign of the eigenvalue in order to have a positive thing. So you're going to have things that are positive and things that are negative. And if you plot this, you have these curves. So I'm just plotting the eigenvalue curves for one of these subspaces. So you have the first one that goes here, then you have another one that goes here, and this in the horizontal lines, I'm just plotting the zeros of the Bessel functions. And you will see that actually from the construction, you see that the limits of these curves are going to be zeros of the Bessel functions. Okay, and then if I'm doing the same for the subspace with a plus, I have to solve like a similar equation in which I have a change of sign and the Bessel functions are changed, and what I get is somehow like a symmetric configuration. I'm having this one now, then this, then this. So you see here already that there is, and you can prove it actually, that there is like an odd symmetry. So this curve is the odd symmetry of this one, and so on. So the picture that you have below is going to be symmetric of the picture that you have above. And this tells you, okay, you can just forget about what happens here and try to understand what happens for positive eigenvalues. This actually is the reason why I was telling before, I want to study the first positive eigenvalue, because I want to study, if I understand well this curve, I'm going to have for free this curve because it's the same. Okay, so our question is going to be related with actually with this first curve. Okay, and now just let me show you just how this picture like evolves. If I take in now more subspaces, then I'm adding these other curves which involve different Bessel functions. So they involve one Bessel function that was in the previous step. For instance, this converges to this, but then you add new zeros of new Bessel functions. Okay, and if you add more, you even see here that the much complicated things. You start to see crossings, etc. But this is essentially what you can do with your computer. And so these are the conclusions that you can get out of playing with this. So first of all, that the eigenvalues can be parametrized as functions of the parameter. And there can be crossings, but you see like smooth increasing curves.
Well, that was in the sphere, right?
Yeah, this is always in the sphere that you have explicit things. Yeah. The other thing that you see is that the spectrum of your operator lives outside this gap that it's from -m to m. You see that the curves are increasing, and you have the symmetry that I mentioned before. And actually it tells you that if you have the kth positive eigenvalue of h tau, it's going to be minus the kth negative eigenvalue of h minus tau. So you have this symmetry.
Sorry, and you can rule out the possibility of a continuous spectrum.
Yeah, because for each tau, you can prove that this is also actually a self-adjoint operator. So the spectrum is going to be discrete, and you can rule out indeed this possibility. This is different if you consider the free Dirac operator or
the
other
Dirac operator indeed presents a continuous.
Yeah, that's the thing. But if you put these boundary conditions, then you have a self-adjoint operator, and then you rule out these possibilities, and you have like discrete spectrum. And this is actually one of the goals of this study, because then you have discrete spectrum, and you want to consider the first positive eigenvalue. Okay, but the most important thing about all of this, or this is something that is already interesting, but something that is interesting are the limits of these curves. Because remember that, as I showed you, the limits are going to be zeros of these Bessel functions, okay? Just some modifications, but
what's the subindex over there?
This is L plus 1/2, because they're going to be Bessel functions of half integer index. Okay, these are sometimes they write it like with the small j. Okay, but okay, so you have this. All the limits are zeros of these functions, except maybe for some special cases that are these ones that are those that converge to m or minus m. Okay, but these zeros of these functions are well known because these are related with the eigenvalues of the Laplacian in the sphere, right? Because the zeros of the spherical Bessel functions are going to be the positive zeros of the spherical Bessel functions are going to be the eigenvalues of the Dirac Laplacian in the ball. Okay, so the eigenvalues of the Laplace operator with zero Dirichlet condition in the boundary. So this is telling us that these curves, that as I was mentioning before, these curves, this family of operators can be connected to some familiar operators. And this is the connection that in the limits, you're going to see an operator that free from elliptic PDS like a lot. It is the Dirichlet Laplacian. So we want to exploit this property. Okay, so this is the property that is going to help us to do something with this shape optimization problem. Okay, but okay, as I told you, this is in the sphere where you can do everything explicit because you have explicit formulas. But you want to do this for a general domain. Okay, it's working, and this is what we do in our work with Nayara, with Luis and Albert, in which we want to prove the same kind of things, but for a general domain. But now we don't have explicit formulas anymore, and we have to try to deal with the things like in a different way. Okay, and this is what we prove. So we prove essentially that the same happens. So first, that the eigenvalues can be parametrized, and you have also a series of curves that parameterize the eigenvalues of this family of operators. Then there is still this symmetry, this odd symmetry that I mentioned before, and the monotonicity of the eigenvalue curve. So these curves are going to be monotone increasing, and moreover, we're able to prove an explicit formula even for the derivative. Of course, this is explicit in terms of the eigenfunction, so it's not super explicit, but it gives you something anyway. And then we're able to prove something that is like one of the key things, that is that the limits at plus and minus infinity are either these special cases in which you convert to or m or minus m, or are these numbers here which involve the Dirichlet eigenvalues of the Laplacian now in this general domain omega. So we prove that indeed this operator links Dirichlet Laplacian at both limits plus and minus infinity in some sense with the family of operators that we want to study. Okay, and then thanks to this, we're able to say some things about the shape optimization problem. So the first easy consequence of this, and I'm going to show you in a second how we prove it because it's super easy. It's to prove like a Faber-Cran type inequality for the first eigenvalue for large values of the parameter. So in the limit, as tau goes to infinity, we're able to prove that if you consider omega a set and then you consider omega star the ball which has the same measure, then the first eigenvalue, the first positive eigenvalue, it's smaller than that of the. So the one of the ball is smaller than the one for the general domain. Okay, and then this is at the limit plus infinity, and then we are also able to say something, some partial results at the other limit, in which we are able to relate this kind of Faber-Cran inequality with the maximization of a Rayleigh quotient that I'm going to show you in a second, which involves some integral operators in the boundary of the domain, and this is related to so this is going to be a maximization, but it's restricted. It's restricted onto functions that belong to a certain Hardy space, in the sense that we are taking like traces of functions that solve like an equation which is analogous to the delta bar equation. Okay, for complex analysis. I'm going to show you this in a second more precisely. Okay,
Thomas, what's smooth for you?
What's this?
The domain is smooth. What do you mean by smooth?
Well, actually, for us, what we need to assume actually is that it's C2. that you can have the normal defined and very well defined and so on. So for C2 domains, yeah, I think that we do it for C2 domains. This is enough. Okay, so just let me, because I don't want to bother you with the details, I'm going to skip how do we do this thing with the parametrization. But I want to show you a bit more like the heuristics on why you really get Dirichlet Laplacian. Okay, and that's why also I wrote this equation down there, because if I write this equation now component wise, what I get is this. So I get that minus this operator u, it's equal to lambda plus mb, and the other way around with u. And then remember that this operator squared is the Laplacian, right? So if I apply this operator here, I'm gonna get Laplacian of u, it's equal to this times this guy, and this guy is this one, so I'm gonna get this times u, which is lambda squared minus n squared u. So actually this u and this b solve an elliptic equation in the domain, okay? But the thing is that you have to look at the boundary condition, because in general you have a boundary condition that you don't like, because it's like messing up with normal derivatives, say, and then you change the components u to b. So this is something that it's difficult to understand. But look what happens if I take the limit tau going to plus or minus infinity. Then one of these guys is going to be 0, which is telling me that one of these functions is going to be 0 on the boundary. And that's where we get really the Dirichlet Laplacian. So in the limits, we really end up with having the Dirichlet Laplacian, okay? And then, in order to prove this thing really about the limits, you need to have some compactness that so compactness for this if you want to take like limits when tau goes to plus or minus infinity, but you can do it, and to do it we need to use several tools that I'm not gonna describe here, but it's one of the tools is like to convert this into a integral operator problem in the boundary of the domain in the spirit of this layer potential theory, and then also use the monotonicity of the eigenvalue curve. It is crucial in order to prove that you don't have like non-degeneracy in your problem, so that your function does not convert to 0, and this is really an eigenvalue problem for the Laplacian, okay? But now let me just spend this last 5 minutes, to explain you very quickly how do we solve the shape optimization problem for large values, which is easy, and what do we get in the other limit. So first, this is the notation that I was using before. I have this domain which is omega, and then I have omega star, which is the ball with the same measure. And then I'm gonna denote by this the first positive eigenvalue of the operator h tau in the domain omega. Okay, so now if I plot these eigenvalue curves, I have that the one for the ball that I already showed you before, because you can have it explicitly, it does something like this and converges to the first Dirichlet eigenvalue of the Laplacian in the ball. And then you want to plot the eigenvalue curve for the domain omega, this general domain omega. So if you plot it, you know that this is going to converge in the limit to some, it doesn't matter if it's not the first, but some Dirichlet eigenvalue of the Laplacian, okay? But then you see that you can compare these things, right? Because this is always bigger than the first eigenvalue of the Laplacian in omega, and then you have for the Laplacian the Faber-Cahn inequality that tells you that you have here a strict inequality. And since this is a strict inequality, then by continuity, because you have proved that these curves are smooth, then you can transfer this information to a certain point that, of course, it's not uniform in the domains, and it's not, we cannot quantify it, but we can say that we have this picture. So this is the easy consequence, and you see that it's really easy once you have done all the work to prove this inequality in this limit. What happens in the other limit? Here things are more complicated, because independently of the domain, the first eigenvalue converges to m. So here comparing things is more difficult, and you need to do kind of a first order expansion, okay? And here the first order expansion that we do is something like this. So you have that this eigenvalue behaves as m plus some term which it's like goes exponentially fast to m, and then something of lower order. So this is like, so we have here this constant that is somehow like the slope minus infinity, modulo this exponential, and this is the constant that we want to compare for different domains. So if we have that for the ball, the slope is smaller than for any other domain, then you will have that here, you also have this curve's order. Okay. And this is what we want to study, but this is difficult. But what we managed to do is first, we were able to relate this constant with the maximization, say, of a Rayleigh quotient of this type, where we have here the L2 norm of U in the boundary, and then here we have an integral operator. Well, it involves also this normal thing, but forget about this. But the integral operator that it's appearing here is the convolution of the function with the Newtonian potential in the boundary. Okay, and then, but life is not so easy, and this maximization is not done over all L2 of the boundary, but in a certain projection of L2. And here this projection is given by an operator of this form, which involves just the identity plus this operator here W, that is this principal value operator, which involves somehow the derivative of the Newtonian potential. And the thing that happens is that these spaces, so because here I'm projecting onto the plus, so the operator with the projection with a plus, you can prove that this is a projection, and these two spaces, because you can consider the plus and the minus, are projection onto Hardy spaces, in the sense that the image of this space are traces of the boundary of solutions to this equation when we take traces from inside or from outside the domain. So this is like the generalization or the analogous of the say the usual Hardy spaces in complex analysis, but here in this setting of this much more complicated scenario. But the spirit is the same, and the good thing about these spaces is that okay, they have some structure that we hope to be able to use it to tackle this problem. But the thing that gives us hopes on why this somehow could lead us to the optimality of the ball is that these projections in general are not orthogonal. So the images of these two spaces gives you two spaces that form an angle, and then we are able to prove, and this is very simple actually, that these projections are orthogonal, so the spaces are orthogonal if and only if the domain is a ball. So you have somehow an optimality of something if your domain is a ball, and this gives some hope on this thing, right? That this constant should be optimal if the domain is a ball. But there are some problems here because this is somehow, so it's very complicated, and we still don't know how to relate this with exactly with this this constant here, and we also don't know how to make appear the constraint, the volume constraint that we want to use. But well, this is just work for the future that needs to be continued. And I'm going to leave this here. So thank you for your attention. Any questions?
Maybe about how very big the constraint was not used there for the inequality.
Yeah, I used it because at the limit I'm using the Faber-Clan inequality for the Laplacian, and there you say that among all sets with the same measure, the ball is the one that has the smallest first eigenvalue. So there I used it because I used the classical result, and in the classical result you use this constraint. And the thing here is that you have these integral operators on the boundary of your domain, and you want to try to relate this with the volume constraint, but we still don't know exactly how to do it. Okay. I must say that this is something that is super not recommendable to say, but we have some computations in R2 using some complex analysis theorems like the Riemann mapping theorem that seem to indicate that really the ball is the optimal domain. Okay, in this also in this other regime, but we still have to like manage to glue all the things and prove this thing. And of course, the last program would be okay. At plus infinity you have this, and minus infinity we have also that the ball is the best one. Can this be broken in the middle or not? But of course, we think it doesn't, but I don't know.
Well, I am still wondering about the discreteness of the spectrum. Well, usually for that, you need something like compactness of the resolvent or something like that.
Yeah, you have it here actually. Because if you want to do, you can write the inverse of your operator, and you can for this operator in the domain, and with this boundary condition, you can have like a kind of a representation formula, and you can write like the inverse of this operator, and you see that this really is a compact operator in L2, and then you can prove that really that the compactness is that the resolvent is compact, and then you have really a self-adjoint operator. Yeah, you can do it.
Well, but self-adjointness and compactness are different things.
Yeah, but but you have both things actually.
Okay.
Because you can prove really that yes, that this is self-adjoint, that the resolvent is compact, and then you have really a discrete spectrum that goes to plus infinity.